Hello, this is Dr. Olson again from Meteorology 2010 at Daytona State College. We have been in the middle of Chapter 2 talking about how the atmosphere is warmed, how it retains its heat. We started off talking about energy and heat, what their definitions are, and the different types of heat. And then we've also been talking about the energy budget. In talking about the energy budget, we talked about what it means to have an energy budget. That is, we have a balance of incoming and outgoing energy, and what happens if that energy is misbalanced. If we have more energy coming in than what's going out, then there's a net gain of energy resulting in an increase in temperature. If we have a net loss of energy, more goes out than what comes in, then there's a loss of energy and the temperature decreases. We also talked about the role of greenhouse gases in keeping the energy inside of the Earth's atmosphere, and we also talked about shortwave radiation. With that, which was all those were done in the previous video, and with that we are now ready to talk about the energy budget itself. Okay, let's start off with a very simple example of the energy budget. So we have insolation, incoming solar radiation that's coming into the Earth's atmosphere. Let's say, for sake of argument, that we have 100 units of incoming solar radiation coming in. Well, about half of that energy actually reaches the surface, about 51%. So of those 100 units, 51 units reach the surface of the Earth. Of the remaining 49, 19 are absorbed in the atmosphere. So that means 51 plus 19, that would be about 70 units absorbed either by the atmosphere or the surface. So what happens to the other 30 units? They are reflected out. So that's 30% of the incoming solar radiation is reflected back out to space. Now recall from the previous video when we talked about albedo. Albedo is the rate of reflection. If you go back to that figure in the book, then you'll read that the Earth has an albedo of 30, meaning we reflect 30% of our radiation. On average, this figure is actually a very typical energy budget on average on the Earth. Again, this is a very simplified matter, simplified example. It gets a little more complicated, and I'm going to show you the more complicated energy budget now. Basically, what we had before was just talking about incoming solar radiation and its direct influence on the surface and the atmosphere. But the surface and the atmosphere interact with each other as well, and that's what makes it more complicated. So we have what we started off with, 51 units of solar radiation hitting the surface and being absorbed, 19 being absorbed by the atmosphere. But in addition to that, the atmosphere is also emitting radiation since it has a temperature greater than absolute zero. So the surface is absorbing some of that radiation emitted by the atmosphere. So if we assume that the atmosphere is emitting 96 units of radiation towards the surface, that means that there's a net gain of about 147 units at the surface. Well, the point of the energy budget is to take what we've gained and balance it with what's been lost. So let's look at what's lost. The surface of the Earth, since it has a temperature greater than absolute zero, is also emitting radiation away from the surface, say about 117 units. But then there are also other processes such as evaporation, conduction, convection that allow more energy to be transferred through regular heat processes. All of those added up together should equal the same amount of energy gained by the surface. Now, if we look at the atmosphere itself, we can see something similar. We have 19 units of energy absorbed from the solar radiation, 111 from the radiation given off by the surface, and then we have the heat from evaporation, conduction, convection, also absorbed by the atmosphere, meaning that the atmosphere absorbs 160 units of energy. To be perfectly balanced, that means that the atmosphere also has to emit 160 units of energy. Some of that energy is radiated to the surface, which we already discussed, but some is also radiated back out into space. And then when we look at the atmosphere as a whole, we saw already that there are 70 units coming in. We better see 70 units coming out. Some radiation being emitted from the atmosphere and some from the surface that escapes through the atmosphere. That should balance to the same 70 units that is gained. This is an ideal, perfect energy budget where all the energy that's gained is perfectly balanced with the energy lost. In a situation like this, there will be no change in energy, therefore temperature will remain the same. However, that's not always the case. There is most often a misbalance. That's what results in changes in temperature. So the Earth's surface absorbs 147 units. Let's assume that we only consider radiation. The surface radiates energy away. That would be 117 units from the figure. That means that there's a misbalance of 30 units, meaning that the surface has 30 units surplus of energy. Since there's a surplus of energy, of course, the surface will get warmer. This is actually very typical in the morning and early afternoon when the Earth is a little bit cooler and the sun is shining, we start to warm up. Very typical situation for the surface of the Earth. In a similar situation, we're ignoring all the evaporation, conduction, convection. We're ignoring all that. What would happen in the atmosphere is the atmosphere is absorbing 130 units between sunlight and Earth's radiation, but it's emitting 160 units, which means that there's a net loss of energy of about 30 units. So that's a deficit resulting in a decrease in temperature. Makes sense because often the atmosphere is actually rather cold. So how do we balance this surplus and this deficit? Well, it's already given in this figure. It has to do with these: evaporation and other forms of latent heat, conduction, and convection. In other words, weather. It is weather that helps to finish the balance between energy gain and loss between the surface and the atmosphere. Now, there are certain areas that always have a surplus of energy and areas that always have a deficit. Straightforward, the tropical areas generally have a surplus of energy. The poles generally have a deficit. So we saw conduction and convection, which is weather. That transfers or creates a balance of energy vertically from the surface to the atmosphere. How do we balance this difference between surplus and deficit horizontally from the equator to the poles? Well, energy is going to have to be transferred somehow towards the poles, and that is done also through other types of weather, such as hurricanes. When hurricanes form, they pull energy out of the ocean water, and then those hurricanes move towards the poles, carrying that energy with it. Remember, we call that advection, which is just a horizontal form of convection. And that wraps up the energy budget. The only topic we have left to complete the chapter is seasons, and that will be discussed in the next video. Should you have any questions, as always, please feel free to contact me by email or by phone. I will be happy to answer.